Here on Tiny Matters, we love opening with a historical anecdote. And Sam, for today's episode about deep sea mining, there were a lot of really cool options.
As in, too many to choose. Like, in the 1870s, a Royal Navy ship called the HMS Challenger had its guns taken out to make room for scientific equipment, converting it from a warship to a research vessel. The ship and its crew would spend several years discovering species and structures in the ocean that scientists are still studying today. They also found potato-sized clumps of metal.
We could also talk about the first deep sea mining test, which was carried out by a company called Deep Sea Ventures in 1970 in an area off the East Coast called the Blake Plateau. Their machine acted a bit like a vacuum cleaner, gathering up around 60,000 metal clumps from the seafloor and leaving behind tracks that are still visible today.
And if we wanted to go for something that sounds too wild to be true, we could talk about the fact that, also in the 1970s, billionaire Howard Hughes lent his name to the Hughes Glomar Explorer, a ship 618 feet long set to do some deep-sea mining. Except that wasn't the ship's mission at all. The Glomar Explorer was actually carrying out a secret CIA mission to dredge up a missing Soviet submarine.
So yeah, there are a lot of historical precedents to deep sea mining that we could be chatting about right now. But you know what we can't actually talk about? Any large-scale deep sea mining operations that are currently being undertaken, because there aren't any. While deep-sea mining has been in the news a lot lately, no companies are actually doing it, which led us to a really basic question: why? Welcome to Tiny Matters, a science podcast about the little things that have a big impact on our society, past and present. I'm Deboki Chakravarti, and I'm joined by my co-host, Sam Jones. Today, we're talking all about deep-sea mining, the practice of removing mineral deposits from the ocean floor at depths below 200 meters or over 650 feet. To be completely transparent, I wanted to take on this episode because I feel like I hear about deep sea mining a lot, especially as an industry that's a cause for a lot of environmental concern, but I didn't know much more beyond that.
Yeah, I really knew almost nothing. When I think about mining, too, I always think about stuff that's happening on land.
Yeah, right, exactly. And again, coming into this with so little background knowledge, I was surprised by how far back the history of deep sea mining goes. And while I'm used to the fact that technology and science is slow, I was also surprised by just how slow progress in this industry has been, given how much it's been in the news.
20 years ago, when I started working in the deep sea mining industry, I was told by one of the mining company CEOs that commercial scale deep sea mining was 10 years away.
That's Andrew Thaler, a deep sea ecologist, conservation technologist, and ocean educator who runs an environmental consulting firm called Blackbeard Biologic.
In 2012, we were told that the Solwara 1 mining prospect was 5 years out from full-scale production. That company went bankrupt in 2019.
So to understand why commercial deep-sea mining has been so slow to progress, let's start by getting to know the deep sea.
Generally speaking, the deep sea is the area of the ocean floor that is beyond the continental shelf of any landmass, as well as deeper than sunlight can penetrate. So we're talking about an area of complete darkness, generally speaking, except for some light-producing organisms and some light-producing geologic features, as well as an area of extreme pressure and extreme cold.
There was a time when scientists thought that the conditions of the deep sea would make it impossible for life to exist, that the pressure and temperatures were just too extreme for anything to survive. But when the HMS Challenger undertook its expedition in the 1870s, they found all sorts of creatures surviving far deeper in the ocean than anyone expected.
Large swaths of the deep sea are made up of flat areas of mud called the abyssal plain. But there are also geological structures like hydrothermal vents and cold seeps that give rise to different ecosystems. Whale falls do that too, where the sinking, decomposing body of a whale becomes both home and food to a number of organisms.
Yum.
Tasty. It's a completely different way of life compared to what we encounter on land.
We're talking about half the surface of the planet. So when the question is what's different about the deep sea is the normal part of this planet. All this weird stuff we do on land with like legs and wings and everything, that is the thing that is out of ordinary. That is the atypical way of being alive on planet Earth. Most of the planet's biomass, most of the planet's biodiversity is in the deep sea. So you get a lot of different kinds of animals and a lot of different kinds of microbes and a lot of different kinds of other sorts of weird organisms.
But as we talked about before, it's not just animals down in the deep sea. There are also metals. For example, seafloor massive sulfides that form from the activity of hydrothermal vents are rich in gold, silver, nickel, zinc, and copper, along with some rare earth metals. There are also thick ferromanganese crusts that are rich in cobalt and that form on volcanic rocks on the ocean floor. But when you hear about deep-sea mining in the news, what you're probably hearing about are polymetallic nodules. Basically, there are minerals dissolved in ocean water, but over time they can precipitate and accumulate around structures. And by time, we mean like over millions and millions of years.
Okay, Deboki, I need to interrupt you really quickly.
Fine.
Because I need to share a little nodule fact with you that I learned from our colleague Mike David, who listeners will hear the name of at the end of pretty much, I think, every episode. So this fact actually comes from his 7-year-old, Ellie. And the fact is that researchers have found nodules that they call shark potatoes because they form around shark teeth, including the teeth of megalodon, which was a massive shark species thought to have lived around 23 to 3.6 million years ago. I love the idea of a shark potato.
Yeah, thank you, Ellie, for telling this. This is our tiny
Ellie.
show and tell us from Ellie.
Yeah.
Yeah, and so actually to make that fact go full circle, we mentioned that the HMS Challenger found metal clumps on their expedition in 1873. Those were polymetallic nodules, and they actually cut them open and found shark teeth in some of them. So that means that they found shark potatoes.
Love it.
And those nodules, they can be rich in manganese, they can be rich in cobalt, they can be rich in nickel. They can also be a little bit enriched in copper.
Manganese, cobalt, and nickel are all important components of the batteries running electric vehicles. And as the demand for electric vehicles goes up, so does the demand for these metals. That calls for more mining on land, which is, of course, not great for the environment. So these nodules in the deep sea are supposed to offer up an alternative that can reduce that harm. The nodules are found around the world, and there are huge nodule fields that run thousands of square miles just casually sitting on the abyssal plains. All we have to do is find a way to pick those metal clumps up and bring them to the surface. That doesn't really sound that hard, does it?
There have been some small-scale tests of deep-sea mining, and there are companies aiming to make a business out of it. But there are a few factors that have made it really hard for deep-sea mining to become a large-scale industry. Broadly speaking, those factors are the law, the technology, and the environment. But as you'll see, all three are very interconnected. So let's start with the law.
So there is this treaty called the UN Convention on the Law of the Sea. It's the Constitution for the ocean. It establishes the rules and regulations necessary for member states to gain permission to mine the deep sea. And that's all done through an organization called the International Seabed Authority, which is a UN entity that is tasked with developing the deep sea mining industry as well as preserving and protecting the marine environment.
First, I love that there's a constitution for the oceans.
I know. I love that too. It really made me think of, for any Arrested Development fans out there, of maritime law.
Take to the sea. Second, getting back to Andrew. So second, Andrew told us that the debate over how to actually license the seabed has been going on for almost 30 years. Because an important aspect of this agreement is the idea that resources in the ocean are going to be managed for the good of humankind as a whole. So basically, the nodules are going to belong to you and me and everyone. But another wrinkle in all this is that even though the United States has been following the law of the sea for the last 35 years, it never actually ratified the treaty. And this year, the U.S. decided that it would start to issue deep-sea mining permits without oversight from the International Seabed Authority, or ISA.
And so what happens when the U.S. issues a mining permit for the high seas in an area that's supposed to be controlled by the ISA? But because we're not members of that treaty, we have our own set of rules. It kind of remains to be seen.
So the regulations around deep-sea mining are murky and complex, which makes it difficult for companies to figure out how to legally do the thing their business is built around. But that's not the only thing holding them back.
If you gave any of the current deep-sea mining companies a mining permit tomorrow and said, all right, go get your nodules, there should still probably be 2 years of development minimum before they'd be ready to actually mine at a commercial scale. The technology is difficult. The ocean is famously infinitely creative in the ways in which it will destroy everything you try to send into it. You know, we're talking about an area of tremendous pressure. Seawater and electronics very famously do not get along well together.
For instance, Andrew told us water is great at absorbing radiation.
So you can't send radio signals through the water, which means, you know, your remotely operated vehicles have to be physically connected to the surface by a tether or an umbilical. And so you have to have, your ship has to have cable handling capabilities that can handle 6 kilometers of heavy, high-throughput cable that's transmitting power and data simultaneously.
And the challenges keep piling on from there. But the thing that probably unifies both the legal complexities and the technological challenges is that third factor we talked about, the environmental concerns.
More on that in a moment. What might a good future look like? Dreaming Against the Machine is a podcast about envisioning a realistic and hopeful future. Each week, the show's host, journalist and astrophysicist, Dr. Adam Becker, will have an earnest and entertaining conversation with a guest about possible futures, seen through the lenses of history, science, and culture. On the first episode, Adam talks with journalist and podcaster Rio Eveleth about who gets to imagine the future, the power that comes with that role, and why certain visions of the future have endured in American culture. New episodes every Tuesday. So subscribe to Dreaming Against the Machine in your podcast app now. That's Dreaming Against the Machine from the Multitude Podcast Collective. All right, back to the show.
If deep-sea mining is meant to be the environmentally friendly alternative to land-based mining, then we need to make sure that it's actually environmentally friendly.
You don't say it, Bucky.
I know, right? One way to do that is through regulations that balance the specific issues that individual nations have around deep-sea mining. The other is through actually ensuring that the equipment that's used for deep-sea mining causes minimal damage. Andrew emphasized to us that deep-sea mining companies are environmentally motivated.
You know, the reality of the situation is if all we wanted to do was mine polymetallic nodules and there was genuinely no concern for the marine environment, you could just drag a beam trawl across the seafloor and scoop up as many millions of tons of nodules as you wanted. A lot of people disagree about whether or not, you know, their environmental motivation is the right set of values, or whether we should be talking about changes in how we consume metals and changes in how we generate energy versus acquiring, you know, new sources of metals. But the reality is that the mining companies themselves are environmentally motivated. When you talk to them, they're talking about developing tools that are better for the marine environment than traditional mining tools would be.
That disagreement over whether or not the mining companies have the right set of values is rooted in part in just how little we know about the deep sea. Again, we're not even 200 years from realizing that there are animals living far beneath the ocean's surface. Polymetallic nodules might be a bunch of metal to us, but they're actually home to a lot of organisms that need structures to attach themselves to.
So on nodules, you'll find deep sea corals growing. You'll find sponges growing. There are animals that live within the nodule fields that don't live anywhere else, so they're clearly depending on the structure that the nodules provide to support some of their ecology. They recently discovered a new species that was called a whiplash squid, and it actually hides. It buries itself kind of among the nodules and leaves two tentacles like hanging up in the water column, and it's basically fishing. It's hiding inside the nodule field and fishing for anything passing by.
Ooh, smart and creepy. I like it. And there are probably a lot more deep sea organisms we don't know about, which makes it really difficult to anticipate how mining will affect them and how those effects will translate beyond the depths of the deep sea. But while deep sea mining isn't happening yet, there have been mining equipment tests that allow us to get some hints at what the effect on the environment could be. Like we briefly mentioned at the beginning of the episode, around 50 years ago, a company called Deep Sea Ventures Incorporated tested a mining rig off the east coast of the United States.
And it was functionally a bottom trawl with a little bit of extra control around it to scoop up nodules. So they went out to an area off the Atlantic coast called the Blake Plateau. The Blake Plateau is a huge stretch of abyssal plain that's sitting on top of a submerged plateau. So it's a little bit shallower than some of the real deep sea. Makes it a little easier to do an equipment test. And it stretches from South Carolina through Georgia to the northern end of Florida. So it's a very large geologic structure. They did this sort of initial mining test. They recovered some nodules. It didn't really go all that well. They were never able to attract a lot more funding, and the company went out of business soon after that. But because they had done that, that represents the earliest experimental deep-sea mining test. And so revisiting that site gives us an idea of what potential recovery could look like over a 50-year time horizon.
We don't have a good sense of what this area looked like before Deep Sea Ventures test, so it's hard to draw definitive conclusions about how deep sea mining may have impacted the ecology of the Blake Plateau. But the areas with mining tracks are notably emptier of life, and there hasn't been any recovery in the 50 years since that test was done.
So, in my mind, when I think about how we approach impacts from deep sea mining, we have to think about the impact to the immediate area where the mining tool is going to pass as a permanent impact. It's not going to recover over human lifespans. It's going to recover over geologic time.
And again, we can't emphasize enough just how mysterious the deep sea is and how much we're still learning about it. For example, over the last decade, scientists have discovered something incredible about the Blake Plateau. It's home to the largest cold water coral reef in the world.
And it's an ecosystem bigger than the state of Vermont. This is a huge coral reef. It's absolutely massive. It very likely may be the largest contiguous ecosystem in the entire continental United States. And we discovered it 6 years ago. So 50 years ago, we were mining on the Blake Plateau under the assumption that there was nothing really there to disturb. And it took us half a century to realize that not a small ecosystem, not like a couple really interesting snails hanging off the side of a rocky outcropping, but the largest ecosystem in the country was sitting right there. And we came within 2 kilometers of just plowing through the middle of it.
It's really important to understand that there are a lot of risks to this environment from deep sea mining. No matter where we're looking, we're seeing impacts to the ecosystem from deep sea mining. And so it's really this societal question of, are we ready to risk the ocean ecosystem for mineral extraction?
That's Michael Dowd, a graduate student at the University of Hawaii at Manoa in the Department of Oceanography. He's been doing research in the Clarion-Clipperton Zone, which is a massive area between Hawaii and Mexico that mining companies have been eyeing as a source of polymetallic nodules.
And as part of the ISA's regulations, these deep sea mining contractors are required to conduct environmental assessments before and during test mining operations. And so that's why a lot of us are doing research in this area to understand what the baseline water column looks like, so that if full-scale mining is to occur, we have something to compare it against.
This work is like the ecologist studying the Blake Plateau, but with that added foresight of getting good before data that will help scientists better understand the effects of deep-sea mining. For Michael, that meant going on 3 cruises to collect samples. The area he was collecting from was so far from land that it took a week just to get there.
These 45-day cruises, they were long and they got really tiring at the end. But it's really cool to see how much you can do, that you're going to this really isolated area and you're living at sea on the water in a floating building for weeks or months on end, and that you're collecting all of this science.
I loved hearing about the science cruise.
Yeah.
It's just really fun and cool to think about a ship that's full of people discovering things about the ocean below them.
Nerdiest cruise ever.
I know, for sure.
So good. I love it. I love it.
It's kind of like a 21st century HMS Challenger. And the goal for Michael was to study what happens with the waste produced by deep sea mining.
So it starts on the seafloor where there's this collector vehicle that's going along and it's sort of vacuuming up these polymetallic nodules. But in the process, it's also collecting a lot of the surrounding sediments, like a couple of centimeters of the seafloor sediment. All of that material is sent into this riser pipe up to the surface where there's a ship that extracts those nodules from the surrounding sediments. But because there's so much of that excess sediment waste being collected, they have to get rid of it somehow so that the ship doesn't sink. And so then they send that material back down into the water column.
When they send that material back down into the water, it forms a plume filled with sediment. Imagine if you were suddenly embroiled in a cloud of small rocks. You'd probably be a bit concerned about what's going on and how it's going to affect your body. Similarly, scientists have a lot of questions about how these plumes will impact organisms living in the ocean.
How is that going to affect animals sort of communicating, because it could impede bioluminescence? The sounds, how might that impact animals that need auditory cues to find each other and mate? And then sort of my research is how might that affect their food web and their nutrition? When you're down at 1,200 meters and there's not phytoplankton, there's not plants that are creating new food sources. So basically, all the food is either coming down from surface waters as sinking particles, or they're carnivorous animals and they're eating each other.
So for Michael, the question is, what could happen if the sediment in these plumes actually becomes food and replaces the sinking particles that organisms at this depth usually rely on? So first, before any mining happened, he and his colleagues looked at the food web made up of larger bits of these sinking particles, the zooplankton that eat those particles, and then the micronectin that eat the zooplankton. They also looked at the nutritional composition of the sinking particles and compared them to what they would later find in the plume.
We found that the plume particles were 10 to 100 times less protein rich compared to the background material, and are in the plume materials in much higher concentrations in the water column compared to the background material. So if full-scale mining is to occur, this could have really severe impacts on the food web, where their nutritionally rich food that they rely on, these larger size fractions of particles, are replaced or diluted with this really nutrient-poor plume material. So these animals could potentially starve. And then this could have impacts further up the water column, where it's not just impacting the animal community down at 1,200 meters, but these animals can serve as the food source for deep diving top predators that are important in commercial fisheries, such as tuna.
Put very simply, stuff that happens in the ocean affects us too. And based on these results, the deep-sea mining company that provided funding for this work, the Metals Company, announced that instead of discharging the waste at the original proposed 1,200 meters, they would now be discharging further down at 2,000 meters.
It sounds like the Metals Company have taken the position that 1,200 meters is bad, so we're going to go deeper to 2,000 meters because it's fine there. But the big thing is that we don't have data. We have some data that goes down to about 2,000 meters that shows maybe there's less biomass down at 2,000 meters, but there are still animals living there. This is still an ecosystem where stuff is happening and that there could be impacts. And we don't exactly understand how this might connect to more surface waters and might have impacts on like commercial fisheries.
So there are all these factors that explain why deep sea mining isn't happening right now. We've got the legal issues and the technological issues, and they all connect to the environmental concerns. But there's also a lingering question. Is deep sea mining even going to be worth it?
Yeah, so, I'm not an economist. I'm an ecologist. I'm not like the world's expert on the finances of deep sea mining, but operating the kinds of commercial scale production that are being proposed offshore will functionally be the largest and most complex offshore operation ever undertaken. The margins aren't all that great.
And on top of the sheer cost of deep sea mining, advances in battery technology might cause demand for these specific metals to go away.
The polymetallic nodules were originally a target of interest because of the manganese, cobalt, and nickel in them, that they're important for electric vehicle batteries. And that's sort of the original push for deep sea mining, was to sort of usher in the green revolution. But now we're seeing that there's a lot of these impacts to the ecosystem from deep sea mining, and these metal sources could come from other places. We can recover critical metals through battery and electronics recycling from waste and historic mine sites, or different battery technologies don't even rely on these.
But if polymetallic nodule mining does end up happening, Andrew proposed two things to consider. The first is, how do we take the results from these smaller test sites and scale them up to understand the kind of impact that decades of mining could have? And the second is, what do we do with the scientific discoveries that are almost inevitable as we get more active on the seafloor?
We've explored almost none of the deep sea floor. I think in total, we've visually observed less than a fraction of 1% of the deep sea floor. And in that less than a fraction of 1%, we've discovered some truly incredible ecosystems that were unexpected. Within the 30-year life of any one deep sea mining prospect, I think the odds of a new ecosystem that was previously unpredicted being discovered is pretty much inevitable. That discovery is guaranteed. And so how do we respond as a society? How do mining companies respond? How does the scientific community respond to, within a mining site, discovering something so totally new?
One of the things I found hopeful while working on this episode is the fact that we seem to be trying to understand the potential harms of extracting from an environment before we actually do it at a large scale. That hasn't necessarily been a common theme throughout human history. It's murky and it's complicated, but it's promising. It's also really high stakes, and the implications go beyond the deep sea.
This is the first negotiation where we've tried to figure out how we're going to manage resources that exist beyond any nation's borders. And this won't be the last one of those. It's going to set the precedent for if companies are ever allowed to do extractive or exploitive industries on the moon or Antarctica. As those industries kick off, they're going to look back to the negotiations happening over deep sea mining to determine the precedent for how we really manage these kinds of resources when no nation has a singular claim to them. And so, it'd be really tragic if the negotiations break down in a way in which it becomes just another free-for-all.
We started the episode out with a few historical anecdotes about deep sea mining, but let's imagine the future. Let's say that Sam and I are still doing this podcast in 50 years. We're in our 80s. We're full of energy.
We're looking great.
We're looking great. We're sounding great. And we want to revisit deep sea mining. Looking ahead, it's hard to predict what we'll have to say about it. We just don't know where the industry is going to go. But I can still imagine working on that episode, and what it would probably have a lot of are incredible stories of the wild deep sea discoveries that scientists are going to be making in the coming decades.
We've barely begun to scratch the surface of this planet. There are animals and ecologic processes in the deep sea that are happening that are incredibly important to the way that the health and the function of this planet works that we haven't even imagined yet. And so, the potential for just sheer discovery in the deep sea is exactly where it was 200 years ago. We are just getting started.
Alrighty, Deboki. Honey show and tell time.
I've got a sort of related one.
Oh, let's do it then.
Okay, cool. Let me actually pull it up. That would help.
No, I want you to just go out fully off the cuff on this one.
I'm going to make it up. Okay, Sam. So I'm going to talk about weird things in the ocean some more.
Ooh.
Yeah, we're going to talk about octopuses.
I love that. Can I just say, like, I stopped, I think it was now like 6 or 7 years ago, I stopped eating octopus because I was just like, I can't do it. They're so smart.
I know.
I can't.
Yeah.
And that was the end of it. So I love them.
Was it a significant part of your diet before?
Not significant, but I don't know. Like, I'm from New England. Like, I'm from the Boston area. I grew up eating seafood.
Right.
And even though octopus is not, like, I wasn't eating octopus like I would be eating, like, cod or something, right? Like, but I definitely...
But you were having it, yeah.
I was having it. Like, I feel like a lot of times sushi restaurants have, like, a really good octopus dish. And so that's really where I've noticed it, where I'll go somewhere and be like, not going to do it.
Can't do it.
Not going to do it. Yeah.
Yeah.
Anyways, sorry, like, that's just a little interruption to talk about my love of octopuses, but please.
Well, I want to see where your feelings about octopus go from here. Actually, it's a very weird transition given what we're going to talk about, but we're going to go with it.
Okay.
Okay. So, octopuses, they've got their 8 arms, right?
They do.
So, researchers were touching the arms of male octopuses. And they were doing it softly. It wasn't like an aggressive thing. But they found that there was this one arm in particular that if they just like gently touched it, the male octopuses like didn't seem to like it. Like they would pull their arm back into their body. It was this one arm. It was their 3rd arm on the right side. So it's called R3.
Oh.
Yeah.
Okay.
It's amazing to also have so many arms that you need to like label them by position and number.
You need to say more than left or right.
Right. This is my R1 arm. This is my L1 arm. Anyway, so the researchers saw this happening and they were like, I wonder if there's like something special about this arm.
Right.
They gathered up a population of 32 male and 41 female Japanese pygmy octopuses. And they found that in this group, 13 of the females had lost this arm. But of those 32 male octopuses, only one of them had. So they seemed to like be at least maybe trying to keep this arm on them.
Right. Can I just ask, like, was it like they were missing other arms too? Or did it seem like they were always getting this one like chomped off or ripped off?
That's a good question. I'm not sure. I think my understanding is like if there was an arm missing, it wasn't going to be this one. Like they were like probably more likely to be protective of it.
Like the males specifically, but not necessarily the females.
Yeah, exactly.
Okay, got it.
Because the other thing they found is like if they put like, I think it was like specifically this kind of like lead sinker object that they would put in the tanks, the females would explore that with their arms and they would like willingly use their R3 arm. But the male octopuses would like kind of try to avoid using this arm in particular. Like the rest of their arms, they would use to explore whatever this new weird thing was. But this particular arm, they were like, nah. Like they seem to be much more protective of that.
Yeah.
Yeah. So for some reason, these male octopuses are protective of this arm. Maybe some listeners can guess where this is going. I'm curious if you can.
Is there like genitalia in this arm?
It is genitalia adjacent. Basically, this arm is important for mating.
Okay. All right. I was like, this just would make sense if there was something reproduction related.
Yes,
okay.
exactly.
All right. I should have said reproduction, not genitalia. Because I was like, that's not relevant in an octopus.
Yeah.
Sort of. Well, I don't know. Yeah. Anyways,
yeah.
Oh
I mean,
gosh.
I'm not going to like dive into all the nitty gritty of like
octopus reproduction
genitalia, but basically, I thought this was really fascinating. This arm is called the hectocotylus.
Okay.
And it's actually like a different arm on the male octopus. Like it has like a different structure and everything. And its job is actually to get sperm to the female during mating. It will actually curl this arm into a tube, force water into the tube, and use that to push sperm into their partner. And so that's why they're so protective of this arm.
So, okay. Yeah, I just looked up a picture of it because I had to. That is fascinating. Right. It was like, no, male octopuses lack external genitals, obviously, but they use this modified arm.
Yeah.
Interesting. So it's like, it's not a penis, but it's not a penis?
Yeah. So they have like a separate penis, but it just like can't actually do this job
What?
And so it needs this arm to do the sperm transfer.
Oh my gosh. Wait, do they have a penis?
I think it's supposed to be like a very small penis. Like it can't reach the female. Like that's how small it is.
Oh my gosh.
And I think the sperm is like made in their head.
Wow.
Yeah. Yeah, there was like a lot of stuff that was like,
Okay.
I don't know if we can get into all this. Like I don't remember what our level of.
Yeah. Oh my gosh, that's so funny. That's so interesting. You know, I think though that the version of a penis is still this arm. Like it has a thing
it might
that's
be.
going. Yeah. So it's
Yeah,
not
because
like
it says in order to push the spermatophore from the penis into the female. So I don't know like where the penis is like on the octopus.
I didn't. I'm like, my search history is wild right now.
Yeah.
Where is an octopus penis? Okay. No, I think it's still this same arm.
Okay.
So the tip of the arm is erectile, allowing it to insert sperm. All right. And it can sometimes break off during mating and remain inside the female. All right. We need to stop. No.
Oh, I did not see that.
Me either.
Maybe that's how that one male octopus lost their arm.
Oh my gosh. Well, sorry, dude.
Yeah.
Okay. This is fascinating, Deboki.
The deep sea or the ocean, maybe not deep sea. I don't know where these octopus were, but the ocean is full of wild creatures, you guys.
It really is. It's incredible. Okay. Well, I'm going to super pivot.
This is also fascinating to me because I was like kind of convinced that you would maybe also bring the story to Tiny Show and Tell today.
This is so a story that I would bring.
Right.
Yeah.
And I just like, I've seen the story. Like, so for the listeners, the way that I approach Tiny Show and Tell is I just have an RSS feed with all my favorite science news sources. And I like go through it and save all the articles. And I'm like, oh, this will be fun. This will be interesting. And this particular research like work, like I saw in so many places
I'm
in the
sure.
last week or two, because everyone obviously is like the octopus arm.
Yes.
The octopus mating arm.
Yeah.
We got to talk about it.
Yeah. Yeah. No, it's like that is like it's clickbait without being clickbait. It's just clickable.
Yeah. Yeah.
Oh
well, I'm
gosh.
glad that I could bring this to you.
Thank you. I love this. And I love that it's ocean related.
Yeah.
Because I went in a completely different direction, like a more medical direction. So
let's go for it.
I wouldn't say it's a downer, but it's like, it's medical. We're not talking about an octopus arm penis, you know?
Yeah,
so it's like there's only so much joy you can get from what I'm going to say after what Deboki just shared. Okay. Let's start with something less fun. Colorectal cancer. Yeah. Yeah. But it has a sort of happy ending to it. Okay, so
that's good.
Yeah, so colorectal cancer, it's the second leading cause of cancer-related deaths. Didn't realize that. The goal, of course, with any cancer, but particularly with colorectal cancer, is catching it early. And a way to do that is with a colonoscopy. You know, Deboki, we're reaching our late 30s, or I guess we're both mid-30s still.
Yeah.
But, you know, time moves fast sometimes.
Sure does.
And so you hear more people that you're friends with talking about, oh, I got to get a colonoscopy or next year or whatever. So colonoscopies, they're invasive, obviously. A lot of people are not so jazzed to get them.
Yeah.
So that is, of course, a barrier to diagnosis. And also in the US, they generally start being covered by insurance, like fully covered by insurance at age 45. But there have been a bunch of reports over the last, I would say, 3 to 5 years in particular, where they're talking about how people are being diagnosed with colorectal cancer younger and younger.
Right.
And so, I mean, who knows, maybe they would change that age. Like, I think probably it makes sense that they would. But that is neither here nor there. So what I want to tell you about is a new study where researchers at the University of Geneva used artificial intelligence, so used AI, to look at patterns in gut bacteria subspecies in stool samples. And in doing so, they were able to actually identify subspecies or patterns of subspecies that are associated with colorectal cancer.
Oh.
And it detected 90% of the cancer cases.
Oh my God.
And so with your typical method now, a colonoscopy, that's on average, a 94% detection rate, which is really good, like very, very good. But the fact that their method detected 90% of cases, and it was using stool samples, which are obviously not invasive, like so much easier to get. I just thought that was really, really cool. Like these are, I know we've had like a few moments on episodes or tiny show and tells or tiny show and tell us bonus episodes where we've talked about like the good things that AI can do, because I think a lot of times we're thinking of like fake images and videos and, you know,
bad writing.
And like really boring wriing where it's like, do you use AI to write your Tiny Matter scripts? No, because no one would listen. It would be so stupid and boring and inaccurate a lot of the time. No. The answer on that is absolutely not. This is coming from our brains.
For better or for worse.
For better or for worse, it's coming from our brains and our own research. But like this is a way that I feel like maybe this is something where like until someone is at the age where they can get a colonoscopy, or if someone's at high risk and they, you know, want to do this test every year, as opposed to like colonoscopies are, I believe, covered by insurance once every 10 years, which seems so minimal. And if you're at high risk, though, I believe it's something like once every 2 years. But like imagine if you could have a test that would give you this early indicator like years before you were going to go back in for a colonoscopy.
Right.
That's not invasive. Yeah. So I just, you know, this is, again, like this is early days, but I think like this is a way in which AI is really valuable and could really, really help people. And
for sure.
Yeah, I just thought this was cool.
Yeah. No, I think that's really interesting. Thanks so much. Like, I think it's like you were talking about like the fact that these case incidences have been going up in like younger people. Like, I mean, we can talk about insurance and what it will and will not cover like forever.
Totally.
And it's frustrating. But I think like having these ways to detect like that are not so invasive is good for everyone and will hopefully like help people catch like earlier than they would have otherwise.
Right. At like stage 1, or when it's not even considered, you know, like I guess it would be stage 1, right? But like able to then, you know, the follow-up would then be like, all right, let's get you in, let's get these polyps removed, let's, you know, and then it's like, you might not even need radiation. Yeah. So I think I'm always like, these kinds of things give me a lot of hope for medicine, because anything that's going to increase access by providing things that are less invasive and less expensive, that's some of the stuff in medicine that I am most intrigued by. Like, those are the sort of technological advances that I am drawn to as someone who has a background in biomedical science, right? Like, I can talk about almost any topic all day in science. Like, I am someone who gets interested in everything, which is why being the exec producer of this podcast is like a dream for me, because I can get interested in literally almost anything in science. I can like go down that rabbit hole, and that is so fun and satisfying for me. Yeah. But I do feel like this is, at the end of the day, if someone was like, you have to choose one thing to like really think about and talk about, this is the kind of stuff that I think it's just like, this gives me hope, more hope for human health and access to like public access to healthcare, right? These kinds of things. So, yeah.
Well, thank you, Sam.
Thanks.
And thanks for tuning in to this week's episode of Tiny Matters, a podcast brought to you by the American Chemical Society and produced by Multitude. This week's script was written by me and edited by Michael David and by Sam, who is also our executive producer. It was fact-checked by Michelle Boucher. Our audio engineer is Misha Stanton. The Tiny Matters theme is by Michael Simonelli and the Charts and Leisure team.
Thanks so much to Andrew Thaler and Michael Dowd for joining us. Go rate and review us wherever you listen. We super duper appreciate it. Also, do you have an episode idea? Email us, tinymatters@acs.org. We'll see you next time.